Welcome to the 8.3 notes for exponential growth and decay. If you are a student who's taken the AP exam in 2021, this is an optional lesson for you. For other years, this would be a required lesson. So what we're looking at is the idea that when a variable's rate of change is proportional to that same variable, then we can use the following equation. This is something that is helpful. We can prove it pretty easily. I'm just going to reword this a little bit. I want to prove that if the rate of change of y is proportional to y, then I can use this equation right here. So let me just kind of walk you through how this would work. So the rate of change of y would be dy over whatever input variable we'll use. We'll use t. Now you could use x or some other variable. If that's proportional to y, proportional means it is equal to y times some constant, which I'll just call k. So k is some constant. Well, I'm going to go ahead and use separation of variables in order to integrate this. So I'm going to divide both sides by y. So 1 over y dy would equal to k times dt. So if I integrate both sides, the natural log of the absolute value of y is equal to, remember k is a constant, it's not our variable. So this would be kt plus c. I'm going to exponentialize both sides in order to isolate y. So y would then equal to c times e to the kt, which is helpful. If you know that the rate of change is proportional to y, then you'll get this formula y equals c times e to the kt power, which, by the way, this is the same as PERT, which you've used before in different math classes. So this is the same formula we used for interest that is compounded continuously, and you've seen that before. All right, here's some examples of how that might be used. If the rate of change of n is proportional to n, so the rate of change of n is proportional to n. Now, I can look ahead and see that the input here is t. This is proportional to n. Now, what this means is that I could rewrite this where the output variable n is equal to c e to the kt power. And this is helpful. I have a couple ordered pairs. When t is 0, t is our input, n is 250. When t is 1, n is 400. And I want to find the value of n when t is 4. Now, from this point forward, this lesson is now just a review of some pre-calculus topics. I'm going to start with this ordered pair right here, and I'll substitute in 250 for n, and I'll substitute in 0 for t. And this will allow me to solve for c because this would be e to the power 0, which is 1. I'm now going to rewrite this as n is equal to 250 times e to the kt, and I'll use another ordered pair that I know in order to solve for k. When n is equal to 400, t is equal to 1. Now what I can do is I can divide both sides by that 400 in order to isolate, to work on isolating k. Right, I want to find out what k is. So 400 divided by 250 reduces to 8/5. It's up to you if you want to reduce that or not. You could leave it 400 over 250, and that equals e to the power of k. Well, if I then take the natural log of both sides, k is equal to the natural log of 8/5. So now I can further customize my equation for n. N is equal to 250 times e to the power of the natural log of 8/5 times t. Well, here's why that's helpful. I now can solve my problem. We now know that we want to use when t is 4. So n is equal to 250 times e to the natural log of 8/5 times 4. Now, it might make more sense to maybe even put that 4 as a multiplier in front. It is not changing the argument 8/5. Okay, it's not 8/5 times 4. It's 4 times the natural log of 8/5. At this point, you could enter this into the calculator, and what we could find out is that n is around 1,638.4. Now, anytime we're talking about radioactive isotopes, so like carbon-14, and of course there are many, many other types, but you'll start hearing them talking about like half-lives, then we can say that the rate of change is proportional to the amount, which means we can use the amount, I'll just use A for the amount, for the output is equal to C times E to the power of KT, that same PERT formula. Carbon-14 has a half-life of 5,715 years. What that means is that however amount you start out with, 5,715 years later, you're going to have half of that. We want to find out the initial amount of carbon-14 if there are 2,000 grams left after 10,000 years. Now, we have to be careful when we write these ordered pairs. They go time as the input and amount as the output, and it's very easy for students to write that backwards. They gave me an ordered pair right here. After 10,000 years, 10,000 is my time, that's my input. I have 2 grams of my carbon-14 dating left. Now there's, what we want to find is the initial amount, which would be times C. I'll use A for amount, for the initial amount. And then they actually did give us one more ordered pair right here. You may not think this is an ordered pair, but it is. After the time of 5,715 years, we have half of the initial amount left. Half of the initial amount left. So because radioactive isotopes have a rate of change proportional to the amount, I can use this formula here. And I can start with any of these ordered pairs that I'd like and see what if they can help me with. Now, these ones right here, you might go, I don't want to start there, but actually this one's a great one to start with. This one's the great one to start with. Let's see why. So what I'm going to recognize, actually maybe I'll even mention this really quickly so you guys can see this. If time is 0, let's just anticipate what's happening. If time is 0, then what we can find out is that A and C are the same thing. This A right here is the actual initial amount, because when we plug in a time of 0, we get that C is equal to A. Now here's why that's helpful. If I then use this ordered pair at the end, if I want to end up with half of A, and the initial amount I just showed you is A, and I put in 5,715 for K, I can cancel that out. And I can say the amount that's left would be half of the original. This is just kind of some proportional reasoning here. If I take the natural log of each side, K is equal to the natural log of 1/2 divided by 5,715. Now, what would be really helpful is if I remember what I'm trying to do is to try to figure out what C, or in this case, I could call it A, actually is. So here's what I'm going to do. I'm going to go ahead and use this ordered pair. So if I rewrite this and I replace K, A is equal to C times E to the power of the natural log of 1/2 divided by 5,715 times T. Well, if I put in 2 for the amount, and I put in 1,000 for time, I'm going to move that time in front of the natural log, or 10,000, pardon me, so that I don't get myself confused. Well, all of this is these are just constant values. So really, I could say that 2 divided by all of that, might want to use some parentheses right here, that's equal to C. And if you put that into the calculator, the C, the initial amount, is 6.726 grams. Talking is hard, sorry. Example 3. A colony of bacteria grows exponentially, and the colony's population is 4,000 at time 0, 4,000 at time 0, and it's 6,000 at time 3. 6,500, pardon me. We want to find the population at time 10. Well, this is the same idea. We're still going to use that same formula, the amount of the colony would equal c times e to the kt, and this is now just an exercise in pre-calculus. If I plug in 4,000 for times 0, we can get that c is 4,000. That happens a lot, by the way, where that initial amount, that times 0, that's often c. It will be c if our equation is exactly this one, okay? It will always work out that way. So a is equal to 4,000 times e to the power of kt. If I then move to the next ordered pair, 6,500 is the output when the time is 3. I can use this to solve for k. So if I divide 65,000 by 4,000, I get 1.625, and that's what e to the power of 3k is equal to. If I take the natural log of both sides, I get that 1.625 is equal, the natural log of 1.625 is equal to 3k. So k is the natural log of 1.625 divided by 3. So if I go back to this and customize further, a is equal to 4,000 times e to the power of t. T is going to be 10 in this last one. Times the value of k, which is the natural log of 1.625 over 3. And in this one, 10 is what t is. I am going to put that in front of the natural log because I don't want to be confused by thinking that I'm changing the argument. If I input this into the calculator, a is about 20,179 bacteria. Oh, look, gave you the answer. Now, you might wonder, why am I rounding this? This because bacteria, it doesn't make sense to have a partial number for bacteria. For things that have to be whole numbers, plants, animals, people, we'll just round them. And what this ended up being was 20,179.228. Use the 0.5 rounding rule for rounding. That's less than 0.5, round down. If it's more than 0.5, you would round up. Number 4, we want to consider this exponential or this differential equation. We are allowed to use the calculator. I want to start by sketching the slope field. Well, you might notice that in this equation of the slope right here, if I plug in a 0 for x, I'm going to get a 0 on the numerator. So what that's telling me is that I can represent 0 slopes as little horizontal segments everywhere where x is 0. In a similar fashion, if I plug in a 1 for y, I will get a 0 on the numerator. And so anywhere where y is 1, I can go ahead and draw my horizontal. For the other slopes, I'm just going to go ahead and pick ordered pairs and just start plugging in numbers. So if I plug in 1, 0, 1 for x, 0 for y, I would get negative 1/2. So I want to make sure my slope looks negative, and it's not super steep there. If I plug in the ordered pair 1, 2, I have a 1 for x, a 2 for y, and I get positive 1/2. Make sure it looks positive. It's not awesome there. If I do the ordered pair 1, 3, 1 for x, plug in a 3 for y, I simplify out to a 1. And I'm going to just kind of repeat that for some of my other ordered pairs. If I do the ordered pair negative 1, 0, I would have negative 1 for x, 0 for y. I get a positive 1 over 2, so a positive 1/2 for my slope. If I plug in the point negative 1, positive 2, I have negative 1 times 2 minus 1 over 2, so I get negative 1/2. And then if I plug in negative 1, 3, I get negative 1 times positive 2 on the numerator divided by 2, which is negative 1. So there's the slope field. Do you have to show work on a slope field? No, you do not have to show work on a slope field. Okay, that's one of the very few times that you don't have to. You certainly could. You could see I had some work over here, but you don't have to. Part B, let y equals f of x be the particular solution to the differential equation with the initial condition of 1, 3. We want to write an equation of the tangent line to that graph at the point 1, 3. Well, if I'm writing an equation of a tangent line, remember the two things I need are a point and I need a slope. and I need a slope. Well, the slope I can find because they gave me an equation for slope. dy over dx, I would use x times y minus 1 over 2, and I'm just going to evaluate this specifically at the point 1, 3. So this would be 1 times 2 minus 1. Oh, I just did this earlier. That's funny. If I do the 0.13, you might remember I got a slope of, oops, this is 3 minus 1. I get a slope of 1. So the equation of the tangent line is y is equal to 1 times x minus 1 plus 3. That's this first part. They also said use it to approximate f of 1.4. So what I'm going to do is I'm going to substitute in 1.4 for x into my tangent line, and then I can use a calculator to help me with that, but f of 1.4, which is the same idea as the output, which is y, is 3.4. Part C, I want to find the particular solution to the differential equation that I'm working with. You might remember it's this one, dy over dx is equal to x times y minus 1 all over 2, using this initial condition 1, 3. So what I'm going to do is I'm going to go ahead and start by separating out my variables. Now this y minus 1 is grouped together, so I do have to be careful here. I remember I'm using typically multiplication or division to try to separate this. So I'm happy where the dy is. The dx, I'm going to move to the other side, so I'll multiply both sides by dx. I'm happy with this x, and I'm happy with this divided by 2. Those are on the correct side. But this y minus 1, I need to divide both sides by y minus 1. Now that the variables are separated, I can integrate. This would be the natural log of the absolute value of y minus 1. And if I use the power rule over here, let's see. This would be 1/4 x squared plus c. I'm now going to exponentialize both sides. When I exponentialize both sides, I get y minus 1 is equal to c times e to the 1/4 x squared. And if I move the 1 over, y is equal to c times e to the 1/4 x squared power plus 1. My ordered pair has an output of 3 and an input of 1. I'm going to move that 1 back over. 2 would then be equal to c times e to the 1/4 power. So c is 2 divided by e to the 1/4. Or we could think of it as 2 times e to the negative 1/4. So if I go back to where I plugged this in, I had plugged it in right here. That's where I need to go back to. Then for my answer, y is equal to c, which is 2 times e to the negative 1/4, times e to the positive 1/4 x squared. You might notice these have the same base. Because these have the same base, what I can do is I can go ahead and write them with that same base and add the exponents together. You might wonder, is that required? The answer is no, it's not required, but if this were multiple choice, this is how the answer would likely be written, rather than keeping these two bases that are the same together. The next few problems are extra practice, and so maybe pause the video, and then when you are ready, you can go ahead and restart it and see how it goes. All right, for number 5, let's see. We had already solved from number 2 a similar problem of this. Since we have a half-life of 5,715, what that means is that half of the initial amount is gone. You might remember the initial amount we could call C. Okay, and if there are 5 grams left after 40,000 years, just be careful to make the time the input variable. And so if I use my equation, my amount here is equal to C times e to the power of kt. If I use this equation, then half of C, my amount, my output, is equal to C times a to the 5,715 times t power. Those cancel out. If I take the natural log of both sides, the natural log of 1/2 is equal to 5,715 times t, and t is the natural log of 1/2 divided by 5,715. So I can rewrite this. Oh, that's not t. Well, hello. T, I already inputted it. These are K. So sorry, I do that often. Okay, so if I rewrite this now, A is equal to C times E to the power of K times T. Now I'll just put the T in the front because I get confused about what's the argument if I'm not very careful. And now I will use this ordered pair where the output is 5 and T is 40,000. Since I'm trying to find C, I will isolate C by dividing both sides by that entire exponential portion. Just be careful when you enter this. You might want to put some parentheses here. And it turns out C is around 639.612 grams. Again, you can pause this one and try it on your own first. And then when you're ready, you can restart this one. All right, so a radioactive element decays exponentially in proportion to its mass. So because of that, we can use this same formula. Half of its original amount remains after 5,750 years. Its initial amount would be C, because if you put in a 0, C would be the output that's left, or C would be equal to A. We've done that before. We have 10,000 grams are present initially. Oh, actually, they told us the initial amount. That's kind of cool. Now, that means that after 5,750 years, if 10,000 grams were initially present, what that means is that we now have 5,000 grams present. That's kind of cool. And we want to figure out how much will be left after 1,000 years. Okay, so starting off perhaps with maybe this ordered pair right here. I'm going to recognize that when I have 5,000 grams left after 5,000, when I start off with, now this is kind of interesting. See if you like this. Let me mention this. We already know, I'll do this first, 10,000 grams are equal to the amount at time 0. So C is equal to 10,000. Maybe I'll start there. So A is equal to 10,000 times E to the power of KT. And now I'll use this yellow ordered pair. 5,000 grams are left when time is 5,750. So if I divide, we could say half. Oh, look, half-life, half. That's not an accident. Is equal to E to the 5 to the power of 5,750K. I'll take the natural log of both sides and divide. So K, our constant, is the natural log of 1/2 over 5,750. Something that is true that you can use is that with this exponential growth and decay, it will always equal the natural log of 1/2 divided by the half-life number of years. It will always work out that way. You may have noticed that because this is our third one doing that. Okay, I'm going to now go back and customize here from this point. So my amount is equal to 10,000 times E to the power of, I'll put the T in the front, times the constant of natural log of 1/2 divided by 5,750. And now I'm going to use T as 1,000. So the amount remaining is 10,000 times E to the power of 1,000 times the natural log of 1/2 divided by 5,750. Be careful inputting it, but at this point you just type and you get 8,864 grams. And that is the end of our lesson.